All right, so in this video, here's our guiding page. Let me find a pen. In this video, we're going to do the photoelectric effect. And the name of this homework, this photoelectric effect homework 3.3, is coming from the notes 19. Is it 19? Let me check. Oof, confusal. Light as a wave/particle. So the photoelectric effect is just the idea that your light impacts and can shoot off electrons. So like the photo part, photo is light, electron, so that's why it's called photoelectric. Okay, so those notes were done in a different video. And here's the homework. Now for today, what you're going to want is a calculator. You can use this one. You can use the calculators in my classroom. I'll try and use both so that way you can see how these calculations work. I'm also going to be using several different colors. My black marker, just regular, red, blue, and this yellow color for what we've used so far in the chapter, right? Wavelength, we did blue. Frequency has been in red. These are old notes. Energy, the page after, I was using yellowish orange. And so that's the color scheme that I'm going to be using for the calculations. Okay. A light beam with a wavelength of 183 nanometers. Okay, wavelength 183 nanometers shines onto a sodium metal surface. I'm not going to worry about the rest of this right now. I'm thinking about light that's coming in to a piece of metal. The metal is specifically sodium. I'll deal with the rest in a second. So there's the first part. Part A says to calculate the frequency of this incoming wave. This is the first page of notes that we did where we converted wavelength to frequency. Oopsies, that is not the right page. Let me get a different page here. Oh no, yeah, sorry, that was the right page. So we've got our equations with wavelength and frequency. This is the general one, but we're going to use the speed of light one because it says it's a light wave. We really won't use this one like hardly at all ever. So speed of light equals wavelength times frequency, and the speed of light is always this number. So I'm going to copy, paste this into part A. The formula I'm using off to the side, the speed of light equals wavelength multiplied by frequency. And the speed of light is always 2.998 times 10 to the 8 meters per second. That's the number I'm plugging in. The wavelength is 183, but I've got to make sure that I convert that wavelength because the formulas and equations can't do nanometers, they can only handle meters. So, if you remember my little trick, when you have a 3-digit number, 1, 8, 3, doop, 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 A 3-digit number in nanometers will convert into number point blah blah times 10 to the negative 7th meters. The full calculation again for this, if you wanted to plug it in your calculator, is just that there's 10 to the 9th nanometers per meter, 183 divided by this number equals our answer. So pause it there if you need to watch this calculation, but what I'm going to do is just use kind of my little, I wouldn't say cheater method, but after you've done the problems enough times, you just recognize that a 3-digit number turns into this decimal style to the negative 7th power meters. So we're going to make our life simple. Okay, that's our wavelength. That's going here. This number is going here, and we're going to be solving for the frequency. So here's, I have a little separator line to keep the equation separate from my work. C equals wavelength multiplied by frequency. We don't know what that is yet, so I'm going to use that variable. To get frequency all by itself, I'm going to divide the 1.83 across so that I'll have, let me use the calculators that we have in class. Parentheses. Always use parentheses when there's an exponent. 2.998 times 10 to the 8th power. To get it to go up to the exponent, you're going to click on this little X with a box, times 10 to the 8th power. Bring it over, boop, parentheses, divided by 1.83 times 10 to the negative 7 power. And this is my frequency. 1.64, I'm going to round that. My frequency equals 1.64. E means times 10 to the 15th power. So there's my answer. That's what the frequency is. Units for frequency, if you forgot, that's okay. Just check your notebook. Back a few pages. Frequency is measured in seconds, but specifically inverse seconds. So s to the negative 1 power. Okay, so here's the frequency. It's going boop, 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 coming in. And the next part says to calculate the corresponding energy. So flip your notes page over to the energy calculations. We're kind of putting all of this together. Our energy options include, we can do energy using the frequency that we calculated, or we can calculate energy using the original wavelength from the problem. Either one's fine, but since we already calculated the frequency in part A, let's just use this equation in part B. So copy, paste the equation here in part B. Again, I'm gonna do this and try and keep each part very, very separate from one another. So the formula here energy equals H times the frequency. H is always going to be 6.626 times 10 to the negative 34. It's a constant. And the frequency we're going to get from part A. Energy equals 6.626 times 10 to the negative 34 times 1.64 times 10 to the 15th power. I just brought that down. And I'm getting for my energy that the energy of, I'm going to label this. This is the energy of the light photon. This is the energy of the light photon coming in. Equals 1.09 times 10 to the negative 18. Energy is measured in joules, so letter J. Okay, if that needs to be watched again, go for it. But pretty much this is just stuff we'd already done, just review. This is page 1 equation, notes page, this was the, let me get the real numbers here. This equation was from 17 notes. This one was from 18 notes. And now we're getting into the new stuff here. So the photoelectric effect is based on the light coming in. Let me get a blank piece of paper. The light coming in has a certain amount of energy. There's an impact on the metal, and if there's enough energy, then electrons will fly off. Let's say we have 100 joules of energy coming in for the impact, and the impact costs 40 joules because every metal has a different cost. Sodium, potassium, magnesium, calcium, they all have a different cost. That cost is called the work function. It has a symbol that looks like this. It's like the letter I with a ring around it. But again, it's just the cost of the impact. How much energy we're losing in the impact. So if 100 came in and lost 40, then the electron would be leaving with 60 joules of energy. It makes sense when it's easy numbers, right? Because see, now what we're going to do is use different harder numbers because the energy, let's see if I can get all of these on the page here. Instead of coming in with 100 joules, it's coming in with, oh goodness, 1.09 times 10 to the negative 18 joules. And the amount that the metal costs is right here. The work function of the metal is 3.69 times 10 to the negative 19. So just like before, 100 minus 40 is 60. We're just using this energy. This is the impact, and we'll be calculating the leftover energy. Okay, so let me write it up here. The energy of the photon was 1.09 times 10 to the negative 18. That's how many joules it had coming in. The sodium metal has a work function of 3.69 times 10 to the negative 19 joules. Put everything in parentheses, that's an exponent. So that minus this. Oh, I did it wrong. Sorry. My bad. Let me do it on the calculator that you guys are going to be using. Okay, 1.09 times 10 to the negative 18 minus 3.69 times 10 to the negative 19 equals this. Okay, that looks better. This is the, let me pick a new color. Do we even have any more colors? There's got to be more colors. Purple. No, that looks too similar to blue. Light green? Okay. So when the electron goes pew and flies off, there's the electron with his little negative charge. When the electron flies off, this minus this equals 7.21 times 10 to the negative 19 joules. All right, so the answer, I lost my green marker. Ugh, good Lord, okay. It's over there. Okay, so the leftover energy here is the answer that we want. I'm still gonna write like the process down below so that you can see it, because what we did is we took 1.09 times 10 to the negative 18 minus the 3.69 times 10 to the negative 19. And this is what equals that leftover energy. There's not really an equation that goes with it. It was honestly just subtraction. So, subtraction. And the leftover energy that the electron is leaving with equaled up here 7.21 times 10 to the negative 19 joules. All right, so pause the video if you need to write that down, but basically we had the wave, we had information about it, we figured out the energy of the wave, we subtracted out the cost of the impact, and now what we have is the energy of the electron going whoop like yeet right off. The last thing we're going to do is calculate the velocity, how fast the electron is whoop, getting yeeted off. And I'm going to use my pink marker for this yeet calculation here. Yeet. Oh, maybe not. That marker is really hard to see. Okay, so the formula that we're going to use here, let me zoom in. The formula for part D is we're going to take the energy that we have left over, and that energy is going to be equal to, let's see, so leftover energy equals 1/2 mv squared. Just the v is squared. The v is the velocity, and the m is going to be the mass of the electron. Let me see if I can sneak this in here. M is mass of the electron. And every single time, for all of the masses, every single electron in the world weighs 9.1 times 10 to the negative 31 power. This is its mass, if you're wondering, in kilograms, but don't worry about the units, just the mathsies for now. Leftover energy equals 1/2, plug in the mass, and we're going to calculate the v for velocity. Make sure your v for velocity doesn't look like this dabbing frequency up here, or you're gonna be in trouble. Don't double wreck yourself. Okay, so leftover equals, let me bring down leftover, 7.21 times 10 to the negative 19. Leftover equals 1/2 the mass of the electron and the velocity squared. This calculation is a little bit tricksy. So first what we're going to do is let's get rid of the 1/2 on this side. I'll write it out for you. Get some new scratch paper. Okay, so everything on the pink sheet is just showing how to do this math. So right here, in order to get rid of the 1/2, we're going to multiply this side by 2. So 7.21 times 10 to the negative 19th. We're going to multiply this side by 2. 2 times that equals 9.1 times 10 to the negative 31 v squared. We're going to divide both sides by the 9.1 to get rid of it on the right. This equals v squared. So once you have this all figured out, then to get v, you'll just take the square root of the answer to that. Okay, So 7.21 times 10 to the negative 19. And I'm timesing by 2, and I'm dividing by 9.1 times 10 to the negative 31 power equals, and I'm going to take the square root of that answer, square root of 1.58, blah, 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 blah. And my velocity here, let's see, this will equal velocity. My velocity, according to the calculator, is 1258815. This is how many meters the electron is traveling every single second. Meters per second. Whoops, I just put that in the wrong spot. My bad. Disregard that. So that's the velocity of the electron. Okay, here's the whole page. I should have color-coded the V over here, the V squared in pink. I'll do it on the next problem. All right, so let's do another one. Let's do, I don't want to do the next one. Number 3, on the back side. Actually, watch this. I'm sneaky. I'm gonna take the problem we just did, because mine's actually not front and back. I just printed it regular style. I'm gonna cut out all of the equations that we just used and show that most of these homework assignments, all but like one question here, uses the same equations over and over again. So here is our, the spacing's not quite the same, but those are going to be our 4 equations. A, B, C, D. So the problem says light with a wavelength of 310 nanometers strikes the surface of cesium, different metal, and photoelectrons are emitted. The work function for the metal is this. This is the cost. So situation just as before. Light comes in, hits the metal surface. In this case, the metal costs 3.36 times 10 to the negative 19 joules for the impact. If we have enough energy, an electron will come off. I'm going to go a little bit faster on this one. 310 nanometers, 3-digit number in nanometers. It's going to be a decimal to the negative 7th power meters. Here's my formula. Speed of light equals, I'm just going to tape this so it quits moving. Tape. Tape. Okay. Speed of light equals that wavelength times the frequency, which I'm trying to find. I'm getting that my frequency is 9.67 times 10 to the 14th power inverse seconds. The energy calculation, energy equals H times that frequency that I just got. I'm gonna bring it down. So the energy of my light photon, the light wave, is 6.408, I guess, times 10 to the negative 19 joules. That's how much energy this wave is coming in with. I'm going to take that number, subtract out the impact. So that minus 3.36 times 10 to the negative 19 equals my leftover energy, which is 3.048, rounding, times 10 to the negative 19 joules. Oopsies. And last but not least, this leftover energy, this leftover kinetic energy, it's called kinetic energy because it's the energy of movement, but it's just leftover energy. So leftover equals 1/2 the mass of the electron, which is always 9.1 times 10 to the negative 31, and the velocity squared. Let's see. 3.048 times 10 to the negative 19 times by 2, divide by 9.1 times 10 to the negative 31. Get an answer, square root that answer. And the velocity that the electron is flying off at in this case is 8.18468 meters per second. The rest of the problems, they are pretty much the same format. The only ones that are a little bit different are 5 and 6, like where they say that it has exactly enough energy to remove an electron, but it has no excess energy. All that's implying is that in most cases, you are coming in with energy, there's the impact, and you leave with excess. Whee! This is saying that you have exactly enough energy and no excess. So what this would be like if I had a block that required 60 joules. I had exactly enough to remove an electron, but I don't, whoopsies, I didn't mean to do that. I do not know, don't have any excess energy. So that one, you'll just take whatever it says the work function is, and that's going to be same with the light energy that's coming in. That'll help you figure out 5 and 6. So since the work function is 6.89 times blah, 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 since that's the work function, that's the wave coming in. Working backwards, if that's the energy of the wave coming in, how could you figure out the frequency or the wavelength? And those are in your notebook, right? Because if you know the energy, plug in H, plug in C, you can find the wavelength. Okay, I'm leaving the answer keys, of course, with either the student teacher that we have or with the substitute. It depends on what period. So this assignment for sure is one that you're going to want to check your work on to make sure that you're getting the right answers.